Hi everyone, I'm Wenxiao Wang. I'm here to present DPlis, boosting utility of differentially private deep learning while randomized smoothing. This is a joint work with Tianhao, Lun, Nanqing, Pan, Dang, and Ruoxi. First, I will brief you some background regarding deep learning. As we know, it has achieved quite some results. In deep learning, we use neural networks to be the parametric models, which can be considered as compositions of parametric functions. The parameters are learned through solving an optimization problem, for which the optimization objectives or the learning loss functions are usually the average of per sample loss over all training data. And the optimization is typically solved using SGD, stochastic gradient descent. Each iteration of SGD basically samples a subset of data and uses the subset to approximate the gradient of the loss function, which is then used as the direction to update parameters. Well, machine learning is about obtaining utility from data, so it is natural to raise concerns regarding if the data are properly protected. Here are two types of privacy attacks. One is membership inference attacks, which is to determine whether a given individual's record is included in the training set of the target model. Another one is model inversion attacks, which is to reconstruct sensitive features of the training data records. The privacy attacks has been shown possible in many cases, which actually motivate the development of differentially private deep learning. Roughly speaking, the notion of differential privacy says that for a function that preserves privacy, its output distribution should not change much whenever only one record of its input data changes. DP-SGD is an approach to make SGD differentially private, so we can have differentially private deep learning. It basically introduced two extra steps into regular SGD: gradient clipping and noising. Gradient clipping ensures that the scale of the data-dependent components get bounded. And in noising, Gaussian noise is mixed with the clipped gradient to ensure differential privacy. DP-SGD is widely applicable. It offers guaranteed differential privacy. But actually, the privacy comes with a price. Because of the noise added to the gradient, DP-SGD typically leads to much lower model performance, and different runs of DP-SGD may result in models that perform differently well. These are the two issues we target in this work. Now let's take a closer look through a toy example. This is an optimization in a 2D space. The loss function is the mixture of two central symmetric functions. So the loss surface contains two local minima, both with near zero loss values. One is flat and one is sharp. You can see the visualization on the right side. Now, let's see what happens when we use DP-SGD to solve this problem. In the middle figure, we plot the final parameters from 100 independent rounds of DP-SGD. We can see that both the sharp minima and the flat minima capture their share of outputs in their neighborhood. However, the sharp minima is not quite noise tolerant. The neighborhood around it offers worse, less stable loss compared to the ones of the flat minima. Consequently, we can see in the right side that the loss distribution has a long tail. Now we see that the flat minima can be preferred. Let's find out what will happen if we can smooth out the sharp minima. Assuming we apply some smoothing, and we have a smooth loss landscapes as in the left side, we can actually have the flat minima to capture the final parameters, just as shown in the middle figure. Since the flat minima offers smaller and more stable loss values in its neighborhood, the smoothing improves both the overall performance and the stability. We can see that on the right. Okay, let's get to how we apply the smoothing. We utilize the randomized smoothing technique. We simply convolve the original loss with a Gaussian distribution. And the sigma smooth here controls the strength of smoothing. This technique is fairly simple, but the question is how we can decide the smoothing strength. Here we introduce an alternative view of the smoothing. Recall that the output of DP-SGD is intrinsically random because of the injecting noise, but the original loss captures only the performance of a single point, ignoring the randomness. A reasonable idea is to instead minimize the expected loss over the corresponding population, as we present here as loss average. Well, comparing loss average with loss smooth, we can consider the Gaussian noise as a rough approximation of the corresponding population. That motivates us to factorize sigma smooth as follows. Basically, we consider it the multiplication of a parameter smoothing radius r and the scale of noise reflected on parameters in every step. We will later see how such factorization is beneficial. Well, and of course, empirically, we can only approximate the expectation with finite sampling. On the right, we have the pseudocode for DP-SGD with DPlis presented. All DPlis does is to tailor the original loss to a smooth version that works potentially better with DP-SGD. Well, previously we have built up some intuitions about how smoothing might help. In this work, we also support the benefits from DPlis theoretically. Due to the time constraint, I include here only a summary of implications. Our results are basically threefold. First, we show that randomized smoothing can indeed lead to a smoother loss landscape. Next, we prove that DP-SGD with DPlis can in fact be more stable than vanilla DP-SGD. Lastly, we show that DP-SGD with DPlis can also generalize better than vanilla DP-SGD. I refer interested audience to check section 4 of our paper for details. We also have DPlis evaluated extensively in many settings, which includes non-transfer settings where models are trained with DP-SGD from scratch, and transfer settings, where we have access to pre-trained non-private models as initializations. Besides, as a representative NLP task, we also have it evaluated on next word prediction on Reddit. What's remarkable is that even with hyperparameters of DP-SGD fixed, DPlis with a fixed smoothing radius and a fixed number of sampling still improves the performance of DP-SGD in all settings. And of course, even more improvements are offered with tuned radius. This won't be possible without a proper factorization of the smoothing strength. In non-transfer settings, DPlis boosts the accuracy by up to almost 6% with tuned smoothing radius R, and up to almost 4% with a fixed radius. In transfer settings, the absolute improvement varies from about half a percentage to almost 6%. On Reddit, which is an NLP task, the perplexity is reduced by at least 50 when using DPlis in all settings. In DPlis, we introduce two scalar hyperparameters, the smoothing radius R and the number of smoothing samples K. Earlier, we showed already that simply setting R and K to be 10 works fairly well across all settings we have. Nevertheless, we present ablation studies of their effects to model performance. On the left, we can see that model performance is approximately a unimodal function of the smoothing radius R, which is a nice property in tuning hyperparameter. This is in fact compatible with the intuition from viewing smoothing as an approximation of the randomness in DP-SGD, as the approximation and the performance both decrease when R is away from the best radius. On the right, we can see that model performance generally benefits from a larger K. This is fairly reasonable since a larger K implies a better approximation of the actual expectation. Of course, more sampling will also means more computational cost. But since it takes no more privacy budget, a practical solution will be to simply select the largest K that is acceptable. If you recall, another issue we target is the stability of performance. We compute here the range and the standard deviation of test accuracy across 5 independent runs for each setting. We can see that with DPlis, DP-SGD can achieve not only better performance, but also improved stability, as it reduces the variations of performance across different runs. Another good thing about DPlis, besides improving performance and stability, is that it tailors only the training loss function. So it is by design compatible with many other strategies to improve DP-SGD. As a proof of concept, here we show the results when combining DPlis with tempered sigmoid. which modifies the activation functions to improve DP-SGD. We can see in the table that DPlis remains beneficial with the other strategy. Here is a bonus. While we have DPlis specially designed for DP-SGD, we surprisingly find that the idea of smoothing learning loss can actually be extended to improve PATE as well. PATE, or Private Aggregation of Teacher Ensembles, is another popular framework for differentially private deep learning, which, unlike DP-SGD, requires access to public data. In PATE, teacher models are first trained independently on disjoint subsets of private data. Then the ensemble of teacher models is used to label the public data in a differentially private fashion. The labeled public data are eventually used to train the final model. Intuitively, PATE introduces label noise in the training, which eventually manifests itself as parameter noise and therefore can be mitigated by smoothing loss function. We can see from the table that the utility of PATE is improved consistently in all settings with smooth loss function. To sum up, we propose DPlis, which utilizes randomized smoothing in the parameter space to boost the utility of differentially private deep learning. As a result, DPlis offers increased performance, improved stability, and also compatibility to other strategies. We consider DPlis as a nice add-on in a wide range of settings. Well, this concludes my presentation. I thank you all for listening.